Okay, let us start with eigenvalues and eigenvectors in continuation with our previous chapter, linear transformation. What we have seen in linear transformation, if t is a function from vector space Rn to suppose Rn again, t is from Rn to Rn, then say we have some input vector x. When t is applied on that function, t is applied on that vector x, so this change in vector x can be represented by A into x, where this A is standard matrix of this linear transformation T. So if I say A into x is equal to y, this y is image of vector x when A is pre-multiplied to x. Okay, so A into x equal to y. Now what if I put the condition A into x, I want x again. So are there any vectors in R2 such that A into x equal to x? Why R2? Because this A is 2 by 2 matrix. So this standard matrix of A, this matrix A is representation of some linear transformation from R2 to R2. So there exists some linear transformation T whose standard matrix is this, and for this function I want collection of all vectors x such that A into x equal to x. So does there exist such a vector? So of course this is going to satisfy for 0 vector. If I say 1 0 2 minus 1 and that is operated on 0 0, the output vector is obviously 0 0. So purposely we are excluding 0 vector and we are interested in finding non-zero vectors which satisfies this equality A into x equal to x. So just try to find out such a vector. So if I just take help of this equation Ax equal to x, let us simplify it. 1 0 2 minus 1, and if I assume that unknown vector is xy and output is again same vector xy. So this implies 1 into x equal to x, 2 into x minus y equal to y. If I just equate, and further this implies this equation is vanished and we remain with only 2x plus 2x minus 2y equal to 0, which further implies x minus y equal to 0, and which gives us x equal to y. It means that capital X such that x comma x, or instead of that you can write t t, where t is any real number. Here you can assume that, here you assume y is free variable t. Say y is equal to free and that is equal to t, so x is also t. Above vector can be written as t times 1 1, where t is any real number. So if I take particularly t equal to 2, this x becomes 2 2. So for this vector 2 comma 2, a into x will be x. Not only 2 comma 2, for 3 comma 3, 4 comma 4, or in general t comma t, a into x will be x. So what happened here? If you see in the xy plane, if this is our original vector x, when pre-multiplied by matrix A, we got the same vector as output. So for a moment, let us write right hand side as a into x equal to 1 into x. A into x equal to 1 into x. Let me call this equation as 1. Now I am also interested in, okay, first let us summarize. So there are infinite number of vectors in R2 such that a into x is equal to x when you have given the above matrix A. Now for the same matrix A and some input vector of R2, can we get a into x equal to minus, can we get ax equal to minus x? We'll do the similar procedure to find out all such x. So my question is, does there exist x in R2 such that ax equal to minus x? Our matrix was 1 0 2 minus 1. 1 0 2 minus 1. Our condition is ax equal to minus x. So consider 1 0 2 minus 1 x y equal to minus x minus y. A into x equal to minus x. If I simplify this expression, it gives us x equal to minus x and 2x minus y equal to minus y. So if I just simplify this, this is 2x equal to 0 and 2x minus, sorry, again 2x equal to 0. So simply we are getting a single equation x equal to 0, and we are getting no constraint on y, so y can take any real value. So I can write x as, hence capital X is equal to 0 comma t, where t is any real number. For example, if capital X is equal to 0 2, let's see what happens. A into x 1 0 2 minus 1, and x we have taken as 0 2. The product of a into x, 1 into 0 0 into, so 0 2 into 0 and minus 2. So the 0 minus 2 can be written as negative of 0 2, or I can say that is equal to minus x. So not only for 0 2, now you can take 0 3, 0 4, 0 minus 1, and if you simplify this, we are going to get ax equal to minus x for all such vectors. So here there are infinite number of vectors there are infinite number of vectors x such that a into x is minus x. So if I just go back to the previous equation, equation number 1, what we can see, for a given matrix X, for a given matrix A, there were infinite number of vectors X such that A into X, the outcome was or the output was the same vector X, whereas in the second case, A into X is minus X. A into X is minus X. So how we can interpret this geometrically? So for a moment that 1 into x and minus 1 into x, if I just replace those 1 and minus 1 value by some lambda, we can say that there are some vectors in R2 to which A is pre-multiplied, the outcome is or the output vector is scalar multiple of the input vector. A into x equal to lambda x. In one case, the value of lambda was 1 and in another case, value of lambda was minus 1. And ignoring the zero vector, there are infinite number of non-zero vector which satisfies such a expression. Geometrically, if you observe, the if this is the x vector, minus x will be, so you have here what happened to this output vector, the output vector had changed the direction, but if you, okay, output vector had changed the direction. If this is x, here we have minus x, and in this case, first case, whatever was the input vector, same was the output vector. Ultimately, what you can conclude, for all such a vectors x, a into x, we got lambda into x. So what we are going to summarize, for a given matrix A, whenever this condition is satisfied, such x is called as eigenvector and this lambda is called as eigenvalue of the given matrix A. Okay. Further part will continue in the next lecture.